Good morning.
Hello.
How is everybody today?
I'm good.
Good. Let's see. 1, 2, 3, 4, 5, 6. I know about 7. And so probably so Keely may be a little late joining us. April. And who else are we missing? Easton. Alrighty. Well, hopefully he'll get logged in. Oh, there he is. Good morning, Easton. All righty, so let's go ahead and take a look at what we had for homework. Some of you may, I did add a place to upload your test if you haven't already. You may have gone ahead and uploaded it with homework, and that is just fine. So anyway, I did upload a test spot, so if you haven't uploaded your test, you can go ahead and do that. And then it looks like we had homework. What day did we, let's see, last week, Wednesday was the 2nd. So we had homework from the 2nd and the 3rd. On the 2nd, it was page 75. So 75 through 77, we had 10 through 44 evens. So we'll go ahead and get ready and go over those homework answers. So page 75 to 77. Let's see.
Miss Jennifer, I forgot to
Yes.
upload those.
That's fine. You can get them uploaded in a bit. Okay, so 75 to 77, 10 through 44 evens, and then we had 82 through 84, 14 through 44 evens. So we'll start with 75. And I'll call out answers, and then if you have questions and you need me to work something, just let me know, okay? Oh, here comes April. Good morning, April. We were just getting ready to go over our homework. And so we're going to start on page 75. We had 10 through 44 evens on 75 through 77. So that's where we're going to start, is checking that homework. Okay, so we'll be starting with number 10. Okay, and we were writing conditional statements in if-then form. Okay, so they gave us a statement and we needed to write it in if-then form. So number 10, it should be if an object weighs 1 pound, then it weighs 16 ounces. Number 12, if a fish is a blue trunk fish, then it lives in the waters of a coral reef. Any questions on either of those? All right, and then analyzing statements, it says decide whether the statement is true or false. If it's false, you have to provide a counterexample. So on the first one, number 14, it says a point may lie in more than one plane. And so that is a true statement. We talked about how if we have we could have multiple planes that a line would intersect through. Number 16, if it is snowing, then the temperature is below freezing. And we know that that is also true. It has to be freezing for it to snow. And then turn the page 76. We're writing the converse of a statement, okay? So remember we talked about how converse is if it's flip-flopped. So instead of saying if P then Q, now we're doing if Q then P. So number 18, the original problem said if angle 1 measures 123 degrees, then angle 1 is obtuse. So your if then, your converse should be if angle 1 is obtuse, then angle 1 measures 123 degrees. Number 20, the original says, I will go to the mall if it is not raining. And so the conditional, if you put that in if then form, it would be if I go to the mall, then it is not raining. So the converse would be if I go to the mall, then it is not raining. Okay. Actually, the converse. Okay, so actually the conditional statement would be if it is not raining, then I will go to the mall. So the converse is if I go to the mall, then it is not raining. All right, rewriting postulates. It says to rewrite the postulate in if-then form, then write the inverse, converse, and contrapositive. Okay, so number 22 says a line contains at least 2 points. So the first thing you had to do is if-then form. If a line exists, then it contains at least 2 points, or if it is a line, then it contains 2 points. The inverse of that would be if a line does not exist, then it is not true that it contains at least 2 points, or you could say then it does not contain at least 2 points. Okay, so remember inverse is not then not. Converse, if it is a line, if a line contains at least 2 points, then the line exists. And then contrapositive is the flip-flop with both nots. So if it is not a line that contains at least 2 points, then the line does not exist. Okay, or somewhere, it doesn't have to be the exact wording, but the main thing is knowing that you're negating and you've got the reverse of it. Any questions about that? All right, and then 24 says a plane contains at least 3 non-collinear points. So the first thing we had to do is put it in if-then form. If a plane exists, then it contains at least 3 non-collinear points. The inverse of that would be if a plane does not exist, then it does not contain at least 3 non-collinear points. Converse would be if a plane contains at least 3 non-collinear points, then the plane exists. And then contrapositive, if it is not a plane, if it is not a plane that contains at least 3 non-collinear points, then the plane does not exist, or then it is not a plane, okay? So like I said, there's several ways to word that as long as you've got the, if then, and then flip-flopping them, negating them, and then doing the contrapositive. All right, so moving on, it says linking postulates. Use the diagram to state the postulate that verifies the truth of the statement. So we're using the little figure off to the side, and it says line L contains points U and T. Let me go ahead and pull this up real quick so we can look at it together. And There we go. All right, so we're using that figure. And so it says line L contains points U and T. So when I'm looking at line L, I know that that's the line that is running right here. Okay, and I can see that it contains points U and T. And so, so for number 30, it would be postulate 6. A line contains at least 2 points. Any questions on that? And then number 32, it says the points S and T lie in plane A. So I have S and T all lying in plane A. And so the one that would go along with that is going to be, let's see, this is 32, postulate 10. If 2 points lie in a plane, then the line containing them lies in that plane. Okay, so S and T make a line and it lies in plane A because points A and T, I mean points S and T are both in that plane. Any questions on that one? And then 34, lines M and L intersect at point T. So I can see where I have line M going that way, line L going that way. They intersect at point T. So postulate 7 says if 2 lines intersect, then their intersection is exactly 1 point. Any questions on that? All righty. Get that erased. Okay. Exercises 35 through 38 state the postulate that shows that the statement is false. Okay. So it says a line, so I'm sorry, no, 36. 2 planes intersect in exactly 1 point. 2 planes intersect in exactly 1 point. So the postulate that tells that that is false is postulate 11. If 2 planes intersect, then their intersection is a line. And then 38, 2 points P and Q are collinear, and 2 different lines, line RS and line XY, each pass through points P and Q. So what tells us that that is not true is that through any 2 points, there exists actually exactly 1 line. Any questions on that? All righty. Then we had over on 77, points and lines in space. Think of the intersection of the ceiling and the front wall of your classroom as line K. Think of the center of the floor as point A and the center of the ceiling as point B. So if we look at number 40, it says, is there more than 1 line that contains both points A and B? So think about if we had the intersection of, like, and last week, I guess it was good timing because we were back in the classroom last week, so we could actually visualize this. And so, so if we had A in the floor and B in the ceiling, then through any 2 points, there exists only 1 line. So that would be, the answer would be no. So it says, is there more than 1 line that contains both points A and B? And the answer would be no. All righty, and then 42, is there a plane that contains line K and point A? All right, so if we took point A and any other 2 points on line K, you would have a plane. So all of those would be contained. So the answer on 42 is yes. Any questions on that? All right, and last one, 44, says to find the inverse, converse, and contrapositive. So for number 44, if x equals y, then 5x equals 5y. So the inverse of that, remember this is where we have not and not, so it would say if x does not equal y, then 5x does not equal 5y, and you could use your equal sign with the slash through it. Then the converse is where we flip-flop it, so it would be if 5x equals 5y, then x equals y. Contrapositive is where we flip-flop not. So it would be if 5x does not equal y, 5y, then x does not equal y. Everybody good with that? All righty. Lots of words on this homework instead of numbers. So let's move on to pages 82 through 84, 14 through 44 evens. 82. All righty. So we had 14 through 44 evens. So we'll start with number 14. We are looking at our perpendicular lines, and we learned that perpendicular lines intersect at a 90-degree angle. So we can see that we have two parallel lines that are perpendicular to one common line. So if we look at number 14, it says angle DCJ and angle DCH are supplementary. Think supplementary, that means if I add them together, they equal 180, so that is going to be true. Number 16, segment FB is perpendicular to line N. So when I look at segment FB, I can see that line N is perpendicular to it, so that is true. Number 18, line M bisects angle JCH. Remember, bisects means that it's going to cut it in half, and that is true. Any questions on those? Then we move over to page 83, biconditional statements. So remember, our biconditional statements are the if and only if. So we're going to look at number 20 says two angles are congruent if and only if they have the same measure. So what we had to do is write it as a conditional statement. We had to put it in if-then form, and then we had to do the converse, okay? So the first thing we had to do is put it in if-then form. So the first thing would be is if two angles are congruent, then they have the same measure. Then the converse of that would be if two angles have the same measure, then they are congruent. 22, we have two lines are perpendicular if and only if they intersect to form right angles. So we have to put it in a conditional statement. So that would be if two lines are perpendicular, then they intersect to form right angles. And then the converse of that, if two lines intersect to form right angles, then the two lines are perpendicular. Any questions on those? All righty. Then moving down to finding counterexamples, and it says give a counterexample that demonstrates the converse of the statement is false. So 24 says if an angle measures 94 degrees, then it is obtuse. Okay, so we could have come up with all kinds of counterexamples, but an example of one would be a 100-degree angle is obtuse, but it's not 94 degrees. So you could put anything in there that about, you know, any other angle that would be obtuse, but that would be over 90 degrees. So we could have, you know, anywhere from 91 to 180 degrees, or I guess 179 degrees would be considered obtuse. But obtuse angles don't only measure 94 degrees. 26, if Terry lives in Tampa, then she lives in Florida. So a counterexample of that is what if she lives in Orlando? What if she lives in Jacksonville? What if she lives in Panama City? Wherever, you know. So Terry could live somewhere else in Florida and still live in Florida, but it doesn't have to be Tampa, Florida. Next section, analyzing biconditional statements. Determine whether the biconditional statement about the diagram is true or false. If it's false, we have to provide a counterexample. So number 28, we have segment SR is perpendicular to QR. If and only if angle SRQ measures 90 degrees. So remember, perpendicular means that they intersect to form a 90-degree angle, so that is going to be true. 30, Angle PQR and angle QRS are supplementary if and only if the measure of angle PQR and the measure of angle QRS equals 90 degrees. Okay, so on this one, we're thinking about what it's saying. So based on what it's just saying, two supplementary angles do not have to just be 90 degrees. One could be 89 degrees and one could be 91 degrees and they're still supplementary, okay? So this statement would be false because you could have other measures that equal 180 degrees, but they wouldn't have to be exactly 90 each. Any questions on that? Alrighty, rewriting statements. Rewrite the true statements in if-then form and write the converse. If the converse is true, combine it with the if-then statement to form a true biconditional. If the converse is false, provide a counterexample. So 32 says, adjacent angles share a common side. So the first thing we had to do is put it in if-then form. If angles are adjacent, then they share a common side. Then we have to write the converse. If angles share a common side, then they are adjacent. Okay, so if it's true, then we're going ahead and making, so think about adjacent angles share a common side. So if there's a common side, they're adjacent angles. So that is going to be true. And so it would be, hold on just a minute. Hang on a second. Okay, so like I said, in the if-then form, if two angles are adjacent, then they share a common side. The converse would be if two angles share a common side, then they're adjacent. And like I said, that was true. And so our biconditional statement, we would put that together to say two angles are adjacent if and only if they share a common side. Okay, so because it's true, then we went ahead and put it in the biconditional form using if and only if. 34, the perimeter of a triangle is the sum of the lengths of its sides. Okay, so we have to put it in if-then form first, where we say if a number is the perimeter of the triangle, then it is the sum of the lengths of the sides. So the converse of that would be if a number is the sum of the lengths of the sides of the triangle, then the number is the perimeter. So again, that is going to be true. So we would put that in a biconditional to say a number is the perimeter of a triangle if and only if it is the sum of the lengths of the sides. 36. Panthers live in the forest. Okay, oh, I guess we lost Easton. Let me get him back in. Okay. So if we put that in if-then form, if an animal is a panther, then it lives in the forest. The converse of that is if an animal lives in the forest, then it is a panther. So we know of all kinds of animals that live in the forest that are not panthers, so that's going to be false. So we have to give a counter example. So you could say, you know, any animal, so a blank lives in the forest, but it's not a panther. So you could say a deer lives in the forest, but it's not a panther. Any other kind of, you know, animal that you wanted to say would be fine as a counterexample. Any questions on that? Alrighty, so we went on to number 44. So then 38, we have mathematical equations or mathematical statements, and it says determine whether the statement can be combined with its converse to form a true biconditional. So look at 38. It says if 3u plus 2 equals u plus 12, then u equals 5. So if we were to solve that, if we were to look at it in its converse, then we would say if u equals 5, then 3u plus 2 equals u plus 12. And it is true statements. So we could go ahead and plug in for our biconditional, 3u plus 2 equals u plus 12 if and only if u equals 5. Any questions on that one? I know it's a little different when we're working with mathematical statements. It looks a little different. Number 40 says if w squared minus 10 equals w plus 2, then w equals 4. So when we flip that and say if w equals 4, then w squared minus 10 equals w plus 2, we find that that is not a true statement both ways. So our counterexample, the converse is true, but the conditional statement is not, because w could either equal 4 or it could equal -3, okay? Because if we with w squared, we could end up having Brett Simpson, how did you get into my Zoom? Does anybody know Brett Simpson?
I've never heard of him.
I don't know how he got into my Zoom. Have we dropped somebody or is everybody here? 1, 2, 3, 4, 5, 6, 7. We got everybody. He just popped in. I don't know how that happened. If something happens and I have to shut down the Zoom, I'll have to start a brand new link. So just if something happens and something came in that's inappropriate, we'll shut it down as quick as possible, and then I'll send everybody a new link. Okay. All righty. So number 40, we said that that was not true, and that that w could end up being -3 also. Is our counterexample. All righty. Let's go to number 42. If y equals -3, then y squared equals 9. And I could flip-flop that to say if y squared equals 9, then y equals -3. And we know that it could be -3, but also it could be 3. Okay, so our counterexample would be a 3. Any questions on those? And the last one was number 44 over on page 84. Rewriting a postulate. Write the converse of the angle addition postulate and decide whether the converse is true or false. If true, write the postulate as a true biconditional. If true, write the postulate, I'm sorry, I just said that. If false, provide a counterexample. So our angle addition postulate says that if C is in the interior of angle ABD, then the measure of angle ABC plus the measure of angle CBD equals the measure of angle ABD. All right, so the converse of that is if the measure of angle ABC plus the measure of angle CBD equals the measure of angle ABD, then C is in the interior of angle ABD. And this is true. So C is in the interior of angle ABD if and only if the measure of angle ABC plus the measure of angle CBD is equal to the measure of angle ABD. Any questions on that? All righty. So moving right along, we are now going to start on page 87, dealing with deductive reasoning. So remember, 2.1 was conditional statements, and we talked about how we've talked previously about inductive reasoning, And so now we're going to be talking about deductive reasoning and how these things are going to be similar but different. All right, so in deductive reasoning, it says in lesson 2.1, you learn that a conditional statement has a hypothesis and a conclusion. Conditional statements can be written using symbolic notation. And I showed you guys this the other day, and so now the book is going to show it to you. I wish they had started out with it about if P, then Q. So basically, we can say that the hypothesis is represented by the letter P. The conclusion is represented by the letter Q. And so, so the example they've given us is if the sun is out, then the weather is good. And so they've identified the hypothesis as P, the conclusion is Q. And so the main thing I want you to see is when it's written like this, with it's read if P, then Q. Okay, so when I have P with the arrow leading to Q, I read that as if P, then Q. Okay, so that means that I can, when I'm using my other ones, my other statements, so like the converse, remember, if converse we switch P and Q, then I would write that as if Q, then P. And so that's where I have Q in the arrow leading to P. Then we talked about biconditional statements. So if it's a biconditional statement, I can do my arrow going forward and backward with P and Q. And that means if P, P, if and only if Q. Okay? So those are the three different notations that we can use here, where we have P then Q, Q then P, and P if and only if Q. Okay, so those are just kind of some shorthand ways of saying all those words. Okay. All right, so example 1 says using symbolic notation. It says we're going to let P be the value of X is -5. Okay, so if that is P, what I'm going to do is, let's see. Put P underneath that, and then let Q be the absolute value of X is 5. Okay, so we've got our P then Q. So it says the first thing to do is write if P then Q in words. So we would write that as if the value of X is -5, then the absolute value of X is 5. So letter A is showing us P then Q. Then it says write Q then P in words. So we know we need to flip-flop it. We need to do the converse, okay? So to do that, letter B shows us that if the absolute value of X is 5, then the value of X is -5. So that would be Q then P. Then we've got to decide, is the biconditional statement here true? Okay, so let's look at that. If the value of X is -5, then the absolute value is 5. Okay, that is a true statement there, right? So if we look at that one is true. But now let's look at the converse of that. If the absolute value of X is 5, then the value of X is -5. And that one is going to be false, okay? Because absolute value of 5 could be -5 or it could be a +5. So that is a false statement. So letter C, the biconditional is false. So the conditional statement was true, but the converse was false. So if they're not both true, then the biconditional is also going to be false. So conditional has to be true, converse has to be true for a biconditional to exist. Is everybody good with that? I have to have 2 trues to make a biconditional true. But just one false makes the biconditional false. All right, so let's go on to page 88. It says to write the inverse and contrapositive in symbolic notation, you need to be able to write the negation of a statement symbolically. So we need a symbol for the negation, and that's what we see here. That's what we see, that our little sign. So the symbol for negation is that little wavy sign, that little wavy line, okay? So if I'm writing not P, then I'm going to have the wavy line in front of P. If it's not Q, then I'm going to have the wavy line in front of Q. Okay, so our regular symbols are P and Q, but if I want to say not, I put the little wavy line in front of it. So if my statement was angle 3 measures 90 degrees, my negation would be angle 3 does not measure 90 degrees, so I would have not P. If my original statement is angle 3 is not acute, okay, so pay attention to this one, because notice that here they've made my statement say not. So it's kind of like if you said not, it's kind of like saying minus a negative and we make it plus a positive. Same thing here, not. If I have a double negative, then that means it's a true, I mean, it's a positive. Does that make sense? So like if it says, so to be able to do not Q, I would have to say angle 3 is not acute. So not would make it is. So if I have a negation to begin with, then when I do the not Q, I'm going to make it is instead of is not. All right, so it says the inverse and contrapositive of P then Q are as follows. The inverse is not P, then not Q. Contrapositive is going to be not Q, then not P. Okay, so if we looked at our inverse, if angle 3 does not measure 90 degrees, then angle 3 is acute. That would be true. But then when I look at the contrapositive, if angle 3 is acute, then angle 3 does not measure 90 degrees. That's not necessarily true, because it could be something that is 120 degrees. Okay, it's not acute, but it does an angle, I mean, it doesn't measure 90 degrees. So here I could have an obtuse angle as well as an acute, and that still be a true statement. Okay, so it says, notice that the inverse is false, but the contrapositive is true. I know this is a whole lot of words and a whole lot of trues and not trues and converse and inverse and negatives and things like that, but it's kind of helping us to get into that mindset. We're trying to develop these reasoning skills, because in a little while when we start doing proofs, we've got to be able to reason through step by step and why I'm saying this comes next after something else. Okay, so we're just kind of trying to train our brain to think about these things. Let's look at example 2. Writing an inverse and a contrapositive. So it says, let P be it is raining, and let Q be the soccer game is canceled. So our if-then statement would be, if it is raining, then the soccer game is canceled. The contrapositive of that, okay? Contrapositive, think about what is contrapositive. That means not Q, then not P, okay? So then I would say, if it is not raining, then the soccer game is, I'm sorry, I've got to flip-flop it. If the soccer game is not canceled, then it is not raining. So I have to flip-flop it and put not. Now the inverse of P then Q is not P, then not Q. So if it is not raining, then the soccer game is not canceled. Okay? So the main thing here to look at, let's see. My conditional statement is going to be P then Q. The converse of that is Q then P. Inverse is not P then not Q. Contrapositive is not Q then not P. Okay? So having a table like that kind of helps us to be able to see this information. So let's look at the information they've put in here. So our conditional is if the car will start, then the battery is charged. So the converse of that is if the battery is charged, then the car will start. So let's think about that for a minute. The first one is true, but could my car not start even if the battery was charged? Maybe there's engine problems. Maybe there's something else that's causing it not to start. It might not necessarily be the battery. So, so we can see that the converse could be false. I mean, that the converse is false. Look at the contrapositive. If the battery is not charged, then the car will not start. That's a true statement. If your battery is not charged, the car is not starting. Then when we look at the inverse, if the car will not start, then the battery is not charged. Again, it could be something else causing the car not to start, so we can see that those are false statements. So it says in the table above, the conditional statement and the contrapositive are true, but the converse and inverse are false, okay? So kind of thinking through these things, we have to kind of start thinking logically to determine, is this true, is this false? So overall, is it true or false statement? Goal 2 is using the laws of logic. Deductive reasoning uses facts, definitions, and accepted properties in a logical order to write a logical argument. This differs from inductive reasoning, in which previous examples and patterns are used to form a conjecture. Okay, so deductive reasoning is using facts, definitions, and accepted properties. Inductive reasoning uses previous examples and patterns to form a conjecture, okay? So the main thing here from inductive and deductive, remember when we looked at our patterns and our numbers and we said, hey, I think based on these previous examples that this is going to continue to be true because it follows the same pattern. That's inductive reasoning. Deductive reasoning is facts and definitions, remember, are going to be meanings that are based on true statements, okay? So using inductive and deductive reasoning. The following examples show how inductive and deductive reasoning differ. The first one says, Andrea knows that Robin is a sophomore and Todd is a junior. All the other juniors that Andrea knows are older than Robin. Therefore, Andrea reasons inductively that Todd is older than Robin based on past observations. Okay, so she's saying, well, hey, Robin and Todd are both juniors. I'm sorry, Robin is a sophomore, Todd's a junior. So therefore, Todd must be older than Robin. Okay, so because she's looked and said, hey, most people that are juniors are going to be older than sophomores. But that might not necessarily be true. Maybe Robin didn't pass a grade, and so she was held back. Maybe Todd got promoted, or maybe Todd started school when he was a little bit younger. You know, just because he's in a certain grade doesn't necessarily mean that he's going to be older. But based on patterns, she inductively decided that Todd would be older than Robin. So let's look at letter B. Andrea knows that Todd is older than Chan. Okay, so she knows that age-wise Todd is older. She also knows that Chan is older than Robin. So she reasons deductively that Todd is older than Robin. Okay, because it's a fact that Todd is older than Chan. It is a fact that Chan is older than Robin. Therefore, using deductive reasoning, Andrea knows that Todd is older than Robin. Okay, so we have two laws of deductive reasoning, and the first is the law of detachment, and the law of detachment says if P then Q is a true conditional statement and P is true, then Q is true. If P then Q is a true conditional statement and P is true, then Q is true. So let's take a look using the law of detachment. It says state whether the argument is valid. Letter A says Jamal knows that if he misses practice the day before a game, then he will not be a starting player in the game. Jamal misses practice on Tuesday, so he concludes that he will not be able to start in the game on Wednesday. This is a valid use of the law of detachment because it's given that both P then Q is true. So if P is true and Q is true, then we know if P then Q. Okay, so he knows for a fact you missed the day before a game, you're sitting out. He missed, so he's going to sit out. Letter B says if two angles form a linear pair, then they are supplementary. Is it true that two angles that form a linear pair are supplementary? Because
Yes.
yeah, so our linear pair is supplementary. But is it also true that all supplementary angles form a linear pair? And that's not true because look at the angles they've given us. I've got two angles here. I've got a 60-degree angle and a 120-degree angle. Those are supplementary, but they are not a linear pair, okay? So we can look at that and see that, hey, if Q is true, if P is true and Q is not true, then it's not a valid conclusion, okay? So then the whole thing is not true. So I was getting ready to say, does this make sense to everybody? And I would hazard to guess that probably it's not necessarily making sense, but you might, but I guess the question is, are you following along okay? Again, these are things that we just have to really stop and think about. It's not a natural thing to go, oh, if P then Q, then, you know, Q then P, and oh, that's true, and the law of detachment, blah, blah. This is kind of all new stuff to us, so we just kind of have to step by step follow through. Again, it's the kind of thing that as you're doing your homework, if you have to look back in the textbook to go, okay, now what was this? Look back. That's how you learn, okay? Because basically by looking back, you're forming those visual images in your head of where you found that information in your book. Or if you've taken the notes and you're seeing it on paper, you're forming that visual image. So when you're trying to recall it later, you remember, hey, this looked like that. So it helps you to remember it. All right, the other one they talked about was the law of syllogism. All right, so first the law of detachment, now we have the law of syllogism. And it says, if P then Q and Q then R are true conditional statements, then P then R is true. So that's that same example that we looked at about Todd and Chan, and who else was it? We had Todd and Chan and somebody else. If one was older than the other one, and this one was older than that one, then this one was older than that one. So basically, if P then Q is true, and Q then R is true, then I can deduce, I can understand that P then R is also true. Okay? So the examples they're using here is with zoology. And so look at our statements here. The first statement is, if a bird is the fastest bird on land, then it is the largest of all birds. My second statement is, if a bird is the largest of all birds, then it's an ostrich. 3 is, if a bird is a bee hummingbird, then it is the smallest of all birds. 4, if a bird is the largest of all birds, then it is flightless. And 5, if a bird is the smallest bird, then it has a nest the size of a walnut half shell. Okay, so we've got to take some of these statements and put them together using the law of syllogism. Okay, so I've got to basically combine, I've got to be able to link 3 of these statements. So let's look at, or I've got to be able to link a couple of them. So let's look at letter A. It tells me that if a bird is the fastest bird on land, then it is an ostrich, okay? Because I've been able to link, if a bird is the fastest on land, then it's an ostrich. Because we decided that these two things are the common thing that's true there. So we said, first of all, if it's the fastest bird, then it's the largest bird. And then we learned that if it's the largest bird, then it's an ostrich. So then I'm able to link fastest bird to ostrich. Does that make sense? The same thing with letter B. If you look and it says, if a bird is a bee hummingbird, then it has a nest the size of a walnut. So again, I've got if the bird is a bee hummingbird, then it has a nest the size of a walnut shell, or half a walnut. So our linking thing here, smallest of all birds, bird is the smallest bird. So we can see here that those two things are linked. And then finally, if a bird is the fastest bird on land, then it is flightless. So again, we had fastest bird on land is flightless because again, it's the largest. So I was able to connect those two things. So again, here we know if P, then Q is true, and Q, then R is true, then P, then R is also true. Any questions on that? Again,
This makes way more sense than the other law, like the syllogism. This it makes way more sense.
makes way more sense, yeah, than the law of detachment. Yeah, so so again, it's the kind of thing where if it gets confusing as you're doing your work, look back. Okay. All right. Now, example 6 says using the laws of deductive reasoning. So it says, over the summer, Mike visited Alabama. Given the following true statements, can you conclude that Mike visited the Civil Rights Memorial? Okay, so it says if Mike visits Alabama, then he will spend a day in Montgomery. If Mike spends a day in Montgomery, then he will visit the Civil Rights Memorial. Okay, so if we're letting Mike visits Alabama be P, then he will spend a day in Montgomery is Q. Okay, so then here, if Mike spends the day in Montgomery, which is Q, then he'll visit the Civil Rights Museum, which is R. So then we're looking to see if P, then R. And so we can see down here, it says, if Mike visits Alabama, then he will visit the Civil Rights Memorial. Okay, we looked at P, then Q, Q, then R, and then we were able to link P, then R. Questions on that? Okay, let's look at our practice. It says if the statements P then Q and Q then R are true, then the statement P then R is true by the law of, what's the law that we just said? That if it's P then Q, Q then R, then P then R? What is that called? The law of?
Deductive reasoning?
Nope, look
Syllogism.
back. Syllogism, good. The law of syllogism. If the statement P then Q is true, and P is true, then Q is true by the law of, what was our other law that we talked about? It's going to be detachment. Okay, so when we look at syllogism, we have P, ooh, not my highlighter. We have P, then Q, Q, then R. So P, then R, okay? So detachment says that if P, then Q, and P is true, then Q is true. Okay. Number 2, state whether the following argument used is in, or if it uses inductive or deductive reasoning. So remember, inductive, patterns, things that you've seen that you're making. It's more than just a guess. You're just not blind guessing. You're making a guess based on experiences and patterns. Okay. Whereas deductive, it's facts and definitions. Okay. So it says, state whether the following argument uses inductive or deductive reasoning. If it is Friday, then Kendra's family has pizza for dinner. Today is Friday, therefore Kendra's family will have pizza for dinner. This sounds like my family. Friday night is pizza and a movie night. So pretty much, you know, on a Friday night at the Fountain House, we are having pizza. So in this situation, is this going to be inductive or deductive reasoning?
Deductive.
Deductive, good. Now, if you wanted to make it, the way that that would change to inductive would be, I went to Kendra's house 3 Friday nights over the summer, and every Friday night I saw them eat pizza. Then based on that, seeing that pattern, that would be inductive reasoning, saying, I think that next Friday they're going to get pizza, okay? But because if it says that this is something that they do every single week, then we know it's going to be deductive because it's a fact that they're doing pizza every single night. I mean, every single Friday. Number 3, given the notation for a conditional statement is P then Q, what statement is represented as Q then P? Think about when we talked about, we've got conditional statements, we have inverse, converse, and contrapositive. Which one of these tells me Q then P?
Converse.
Converse, good. Number 4, a conditional statement is defined in symbolic notation as P then Q. Use symbolic notation to write the inverse of P then Q. So remember, what is my word that I use for inverse? I use not. And remember, my symbol for not is my little wavy line. So I would have, for my converse, is going to be not P, then not Q. Okay. Number 4, a conditional statement is defined in symbolic notation as P then Q. Use symbolic notation to write the inverse of P then Q. Okay, so what did I just do? I skipped over. No, I'm sorry. I just wrote that in the wrong place. I was going, wait a minute, what did I do? So that wasn't supposed to go there. That's supposed to go down here. Not P, then not Q. Okay. Number 5, write the contrapositive of the following statements. Okay, think about contrapositive. I have to flip-flop P then Q, so it's if Q then P, and then I have to put in not with both of them. So if not Q, then not P. Okay, so that's the first thing I've got to think about is what does that mean, contrapositive. So if you don't enjoy scary movies, I'm going to go ahead and label that as P. Then you wouldn't have liked this one. So that's my Q. Now I've got to flip-flop it and put not. So that means I'm starting with Q and say, if you liked this movie, because notice here it said wouldn't have liked. If I've got to use the not version of that, if I've got to use the opposite of would not have liked, then it would be would have liked. So if you would have liked this movie, then you do enjoy scary movies. Okay, so since this is don't, it's going to have to become do, and wouldn't becomes would. Is everybody good with that? I think we've been so used to saying if something, then something, but remember that when I'm negating it, if it's already a not, then it becomes an is, okay? But if it is an is to begin with, then we have to go to is not. So just kind of thinking through that. Number 6, if a ray bisects an angle, again, stop and think bisects, I know it cuts it in half. Then the congruent angles, congruent means they're equal to each other, formed are complementary. In the diagram, angle ABC is a right angle. Are angle ABD and angle CBD complementary? And then explain your reasoning. Okay, so let's think about this for a minute. All right, BD bisects ABC. Okay, we see that.
I need your consent on a few
So
items.
we can see that ABD and DBC are two complementary angles. So I guess it just went backwards instead of the notice here, it says CBD. So you could either name it, so CBD is there, and then we've got ABD there. So because it's a bisector, they are complementary. Because they are complementary, they equal 90 degrees. Okay, so remember 90 degrees complementary. Bisector, cutting a right angle in half, does make them complementary. Then number 7, if F then G and G then H are true statements, and F is true, does it follow that H is true? So let's think about this for a minute. If F then G is true and G then H is true, then does it follow that H is true? So what does this sound a lot like? We're using different letters, but what does it?
I know a syllogism, law of syllogism.
So F then G, G then H, then F then H. Okay, so we said if this is true and this is true, then this is true based on the law of syllogism. Okay. All righty. Let's take a look at some work for you to do. I know you're so excited. Let's go ahead and do pages 91 through 93. Numbers 8 through 48 evens. Okay, 8 through 48 evens. That's what, roughly like 20 problems. All right, let's take a look at our time. Oh, we've gone over on our break time. So let's go ahead and take a 5-minute break, and then we will come back to the next section. All righty. Everybody back?
Yes, ma'am.
Talking to you, dog. I'll let my dog in. She thinks I'm talking to her. She's like, yeah, I'm ready. I'm good. Okay, you gotta go lay down.
All right.
All righty. So in this section, we are reasoning with properties from algebra. And so we've talked about properties. You probably started, I'm trying to remember when you start learning properties like the commutative property and things like that. You start learning properties like in 4th, 5th grade or something like that. And I know that we even started talking about those, you know, pre-algebra, algebra, we still go on about properties. And so basically our properties in algebra help us to know that certain things are true, okay? And so here are some properties. It says many properties from algebra concern the equality of real numbers. So think about like when we are solving equations, we talked about these properties, but we really didn't go in depth at this point for you to be able to go, oh, well, the reason that I can move a negative number by adding it to both sides is because that's the addition property. Well, now we are going to do that. We're going to look at it and break it down and see how these different properties, how actually when we have been solving equations, we've been using these properties all along. We just didn't know how to name them, okay? So it says in the green box, we have our algebraic properties of equality. So it says let A, B, and C be real numbers. Okay, so we know that these are real numbers we're dealing with. And the addition property says that if A equals B, then A plus C is equal to B plus C. That means that if I were to add a value to both A and B, and that value was exactly the same, then they're still going to be equal to each other. Okay, so if A was 1 and B was 2, and I added, I'm sorry, if A was 1 and B was also 1, because A equals B, then I could add a number to each of them that's exactly the same, and A is still going to equal B. Same thing if I subtract. If A equals B, and I take a value away from both of them that is the same, then A is still going to equal B. The multiplication property tells me that if A equals B and I multiply them both by the same value, then A is still going to equal B. Because A times C equals B times C. Division property, okay? This one has one little thing here because it says if A equals B and C does not equal 0. Remember, I can't divide by 0. So I have a condition here that if A equals B and C does not equal 0, then I can divide A by C and I can divide B by C and they're still going to be equal. So those are properties that we have worked with to be able to solve equations. Now we're looking at a few new properties that, that we may not have really thought about much, but basically the reflexive property just says that for any number A, then A equals A. Okay, A is going to equal itself. The symmetric property, okay, think about symmetry, think about how if it's this, you know, they're kind of mirror images. So it just says if A equals B, then B equals A. Okay, that's symmetric property. Transitive is a lot like our law of syllogism. Transitive says that if A equals B and B equals C, then we know that A and C are also equal. Okay, that's a lot like that property we just looked at a moment ago. And then the substitution property says that if I have a value, if I know that A and B are equal to each other, then I can substitute A for B and I can substitute B for A in any equation or expression. Okay, so one of the things I wanted to mention is my weekend did not go the way I had hoped it would, and I did not get nearly as much work done as I wanted to get done over the holiday. So I have not written in my blue folder yet. So I'm going to work on that this afternoon when I finish with my next class. I'm going to work on blue folder and I will send you pictures of my blue folder. One of the things that I want to tell you that I'm going to start doing once we get our blue folders ready is that I would say, hey, this is a blue folder item. This is an item that you want to put in your blue folder. Okay. So like I said, I'll do my blue folder this afternoon and I will send that to you guys so you can start working on yours. And then we'll get it all caught up. And then I'll say, hey, this is something you'll want to put in your blue folder because this is something you're going to refer back to. Because as we start writing proofs, we're going to be using some of these terms. And it's going to be a whole lot easier to flip back in your folder than having to go page after page after page in your textbook. Okay? All righty. So then it says properties of equality along with other properties. Properties of equality along with other properties from algebra, such as the distributive property, can be used to solve equations. So again, distributive property here tells me that if I have a number outside of parentheses, A, it would have to be multiplied by both B and C. And so those of you that have had me before know that when I use distributive property, you will always see me draw arrows because I know I need to multiply A times B and A times C. Okay, that is just a visual cue for me so I do not forget to multiply that number outside by each term inside. So remember, whether it's 2 terms inside the parentheses or 15 terms inside of the parentheses, I have to multiply that number outside by every single term inside parentheses. Okay, so that's distributive property. And then it says, for instance, you can use the subtraction property of equality to solve the equation x plus 3 equals 7, because what I'm going to do is I would subtract 3 from this side and subtract 3 from this side. The subtraction property tells me that if I subtract the same amount from both numbers, then it's still going to be equal. Okay, so when I subtract 3 from each side, I end up with x equals 4, and that's because of the subtraction property. So now we're going to kind of go through this. Okay, so basically, if I'm starting off with 5x minus 18 equals 3x plus 2, you'll notice that every time we start out, they call this the given. The given is what information they have given us and told us to be true, okay? Then we're going to go through the steps to solve and identify what properties we use for this, okay? So they started with 5x minus 18 equals 3x plus 2, and you can see here that because they subtracted 3x from each side, I've ended up with 2x minus 18 equals 2, and that was because of the subtraction property of equality. Then to get from 2x minus 18 equals 2 to 2x equals 20, I had to add 18 to each side, so that links with the addition property of equality. And then I have 2x equals 20 now, and to get to x equals 10, I have to divide both sides by 2, and that is the division property of equality. Okay? So all we're doing here is we're taking stuff that we did in algebra, and we are putting names to why we did those steps. Okay? Let's look at the next one. 55z minus 3 times 9z plus 12 equals a negative 64. So if I was going to solve this problem, obviously the first thing is my given. But notice, before I can start moving anything from side to side, I have a 3 outside parentheses. So that means I need to distribute that. Okay? So I use the distributive property first, and I ended up with 55z minus 27z minus 36 equals negative 64. So the first thing is applying the distributive property. Then the next step, notice they call it simplify, because what they did is they were able to combine these like terms right here. So they're calling that simplifying. So you could either call it combine like terms or simplify, but that's what they did in that step. So now they have 28z minus 36 equals negative 64. I know that my next step would be to add 36 to each side, because my whole process, I'm trying to get z by itself. So I'm having to undo the equation to get to z. So this was our addition property. I've got 28z equals negative 28, so I need to divide by 28. Whoop. Divide by 28 using my division property. So I've ended up with z equals negative 1. Any questions about doing that? about naming each property as you go. Just remember, you always start out with your given, and then all you're doing is naming those properties. All right, so it says using properties in real life. Before exercising, you should find your target heart rate. This is the rate at which you achieve an effective workout while not placing too much strain on your heart. Your target heart rate, R, in beats per minute, can be determined from your age, A, in years, using the equation A equals 220 minus 10 divided by 7, R. Okay. So what it's saying here is we need to solve the formula for R. This is what we call, oh gosh, I've lost my word. In algebra last year, we, oh my goodness, it's when you're solving the equation for a specific variable. You're not putting in values, you're not solving for a value. I've totally lost my word. I'll have to think about it and figure it out. Okay, so basically I'm starting with this equation here, and I'm wanting to solve for just R. So what I've got to do is to get to that point, I have to look at all the steps that I've got to start with. So we can see that we have our given, which is our starting equation. Now, what I want to do is the first thing I'm going to do is need to, I've got A equals 220 minus 10 over 7 times R. Notice what they did first of all is they went ahead, why did they do that? Oh, okay. They're trying to go ahead and get R on the left-hand side, first of all. So y'all know that how I am about, I like my variables, whatever I'm solving for, to be on the left-hand side. So that's why they went ahead and added 10 over 7R. Add 10 over 7R. And the addition property of equality lets me do that. So now I have A plus 10 over 7R is equal to 220. I want to move that A that is with that, so I'm going to have to subtract it because it's positive. If it's positive, I use subtraction. If it's negative, I use addition. So I'm going to subtract A from each side using the subtraction property. Now notice that I have got 10 over 7R equals 220 minus A. You can do one of two things here, and it's going to end up being the same thing, okay? What do we call when I have 10 over 7 and 7 over 10? What are those called?
Reciprocal.
Good, reciprocals. And remember that a number times its reciprocal is going to equal what?
1.
1. 10 times 7 is 70, and 7 times 10 is 70, and 70 over 70 is 1. Okay? So basically, I can do this when I'm trying to move a fraction from a variable. I can just multiply by the reciprocal because that's the same as multiplying by 1. Okay? Now, the other way that you could do that, I'll go ahead and come over here. If that's just not something that you remember, then one of the things that you could do here, I'm gonna go ahead and rewrite the problem. 10 over 7R is equal to 220 minus A. Okay, so one of the things I could do here is to eliminate my denominator. I can multiply by my denominator. Okay, so my 7s would cancel here, and I would end up with 10R is equal to 7 times 220 minus A. Okay, then I would have to divide by 10, Those cancel, so R is equal to 7/10 times 220 minus A. You're going to get there exactly the same way. You can either multiply by the reciprocal, or you could multiply by the denominator first and then divide. Okay, you're going to get the same thing. Obviously, it's faster and more, more easy to multiply by the reciprocal. But all right, so we ended up with, now we have solved for R. Okay, and that was our goal. And so multiplying by the reciprocal, we use the multiplication property. And that gave it that by doing that, we saved ourselves 2 steps, because here we would have to use the division property, and here we're having to use the multiplication property. All right, so the next one says using A equals 16. Okay, remember our whole thing here was dealing with calculating heart rate, target heart rate. And so if we said that a person's age is 16, we are plugging in A. So we start with our given, just like we always do. Then remember, they said A is equal to 16. So this is the substitution property, because I know if A equals 16, I can put 16 in for A. All right. So once I've done that, then I can just simplify by multiplying 20, or subtracting first 220 minus 16, and then multiplying that by 7/10. Okay. Remember, we can use a calculator. So we know that 7 divided by 10 would be 0.7. So I would subtract 220 minus 16 and then multiply by 0.7, and we end up solving to find a rate of 142.8. So it says from the table, the target heart rate appears to decrease as a person ages. So by using that, you can see that if you're 20 years old, your target heart rate would be 140. 30, 133. If you're in your 40s, 126, 50s, 119, 60s, 112. So we can see that those rates are decreasing as age increases. So that is called an inverse relationship, because as one goes up, the other goes down. All right, now we have a few more properties that will end up being in our blue folder. And these are geometry properties, okay? These are properties of equality that apply only to geometry. And so the reflexive property says for any segment AB, AB equals AB. When we're talking about angle measure, for any angle A, the measure of angle A is equal to the measure of angle A. All right, so basically reflexive, just like we looked at the reflexive property up here, where we said A equals A. When we're dealing with geometry, we're saying that segment AB is equal to segment AB, and angle A, the measure of angle A, is equal to the measure of angle A. The symmetric property, just like we looked at symmetric with addition, if AB is equal to CD, then CD is equal to AB. And then transitive, just like we said, if A equals B and B equals C, then A equals C. In geometry, dealing with segments and angles, we have if AB is equal to CD and CD is equal to EF, then I know AB is equal to EF. And if the measure of angle A is equal to the measure of angle B, the measure of angle B equals the measure of angle C, then the measure of angle A is equal to the measure of angle C. And this is similar to that law of syllogism that we looked at earlier. Okay. So since you started solving equations back in 6th, 7th grade math, pre-algebra, algebra, all that good stuff, applying properties to our steps of solving the equations comes a little more naturally. And that's why we started with that, because we can see the application. We can apply, hey, I subtracted 3 from both sides, so that's the subtraction property. Hey, I divided both sides by 2, so that's the division property. Now what we're going to be doing is using that same logic to apply these properties of equality for geometry to geometric situations. Example 4 says we're going to use the properties of length. And it says in the diagram, AB is equal to CD. So we can see that we've got these two segments on our line, and it tells us we are given that AB is equal to CD. So again, we start out with the given. Now we can see that we could use the addition property of equality, that if we wanted to add BC to AB and add BC to CD, that we could do that using the angle property of equality. I mean, the addition property of equality. Okay. So let's look at the segment addition postulate that says that AC is equal to AB plus BC. Okay. So we know that AC is equal to AB plus BC. And we also know that BD is equal to BC plus CD. Therefore, AC equals BD. Okay, so we started out that AB is equal to CD. We ended up showing that AC is equal to BD by going through these steps and showing how I can relate the information to each other. Okay, it's going to be uncomfortable as we're working through these. This is what we're getting into, starting to write proofs. And that's what writing proofs does. We start out with one thing and we want to prove something else, but we've got to figure out what are all the steps to get to that point. And we've got to use these properties, we've got to use these proofs and theorems and things like that to be able to get to that point. Okay, so right now we're just trying to see, how do you get from point A to point B? I've got to go through all these steps. All right, so that was using properties of length. Now let's look at example 5 using properties of measure. The example is auto racing. The Talladega Speedway racetrack in Alabama has 4 banked turns. Y'all know banked turns is kind of where they go up on the side, which are described in the diagram at the left. Use the given information about the maximum banking angle of the 4 turns to find the measure of angle 4. So notice all of this information right here is what I have been given. Okay, so you can see that in our first given, it says the measure of angle 1 plus the measure of angle 2 is equal to 66 degrees. That's what they told us right here. We also were given that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 99 degrees. Okay, so we're given both of those pieces of information. Okay, so now what I can look at is if I've taken 66 degrees from my first bit of given information, which was 1 plus 2, then basically I'm substituting 66 degrees for 1 plus 2, and then I'm going to add in the measure of angle 3, which equals 99 degrees. So that's going to be the substitution property, because what I've done is I have substituted 66 for measure of angle 1 plus measure of angle 2. Does everybody see that? That I have taken away in this step right here, I took away measure of angle 1 plus measure of angle 2, and I substituted the value of 66 degrees. So now I can subtract 66 degrees from each side to end up with the measure of angle 3 is 33 degrees, and I did that by using the subtraction property. Okay, so now I know the measure of angle 3 is equal to 33 degrees. So again, I have given information here. The measure of angle 3 equals the measure of angle 1. They told me that there. And the measure of angle 1 equals the measure of angle 4. Therefore, the transitive property tells me that 3 is going to be equal to 4. So that's what I have there. So I know that if angle 3 is 33 degrees, then angle 4 is also 33 degrees because I substituted that information. Okay, so as we go through these, we're going to take it really slow as we go through proofs. We're going to kind of look at what information you need to have. And I think, again, a lot of doing proofs to me was magic. Again, I didn't understand that it was just following logic and going with what information you've already been given to be able to get from here to here. Okay, so remember in our problem, it ultimately told me what I'm looking for. It told me I am trying to find the measure of angle 4. So that's how I know that's how I know that that's what my goal is. That's where I'm trying to get to. So I'm using all this information they've given me to begin with to be able to go step by step to get to that last thing. Okay? We're going to take it slow and we'll go through it. Okay? Let's look at our practice here. Okay, for vocabulary check, it says name the property that makes the following statement true. If the measure of angle 3 is equal to the measure of angle 5, then the measure of angle 5 equals the measure of angle 3. What did I say that kind of is like a mirror? Which one, which property?
Symmetric.
Symmetric, good, symmetric property, okay? We know about symmetry. We know how your face basically has, you know, if we had an invisible line or we, you know, or if we had an actual line down our face, then we know we've got, you know, it's symmetric. So, so thinking about symmetry, mirrors, things like that. So when we see that all we've done is flip-flop the 5 and 3, that's the symmetric property. Okay, let's look at number 2. It says, explain how the addition property of equality supports this statement. If the measure of angle JNK equals the measure of angle LNM, then the measure of JNL is equal to the measure of LMN. Okay, let's look at that for a minute. JNK is equal to LNM. The measure of JNL is equal to the measure of KNM. What do you think? So think about this for a minute. Basically, we have let's see how I want to kind of highlight this. If I have this angle is equal to this angle, okay? If I add this same measure to both sides, I add it to this one, then it's going to be equal if I add it to that one too, okay? Because I'm adding this same exact measure. So let's say if I did it with, I'm going to make up some numbers real quick. Let's say that this angle measures 35 degrees. And this one measures 35 degrees. Okay? And then this measure here is 45 degrees. Then that means if I add 35 plus 45, meaning I'm doing JNL, then that's going to be the same as KNM because I'm adding 45 plus 35. Okay? So here, 80 equals 80 degrees. So if I start with two equal angles and I add another angle to both of them, I'm going to end up with equal measures. So that's what it's describing here. And so the addition property of equality tells me if I add this same amount of 45 to equal angles, then I know that the bigger angles are going to be equal to each other as well. Does everybody follow that okay? If I'm ever explaining something and you don't understand, please let me know, and I'll try to find another way to describe it, okay? Likewise, in number 3, it says explain how the subtraction property of equality supports the statement of JNL is equal to KNM. So let's get rid of all this so we can look at it cleanly. Okay, so it's saying that JNL, I've got this angle, is equal to KNM. Okay, we know that those two are equal, but I could subtract KNL from both of them and find that JNK is equal to LNM, because I would be subtracting that same amount from both of them. Okay, so the first one we looked at, we added the same amount, so we know that the larger angles end up equal to each other. But in this one, we started with the larger angles, subtracted the same amount, and our smaller angles are equal to each other. All right, in exercises 4 through 8, match the conditional statement with the property of equality. If JK equals PQ and PQ equals ST, then JK equals ST. Which one of those? Would it be addition, substitution, transitive, symmetric, or multiplication property?
Transitive.
Good, transitive. So number 4 is D. Number 5, if the measure of angle S is 30 degrees, then 5 degrees plus the measure of angle S is equal to 35 degrees. Which property would that be? It's going to be our addition property. Okay. Oh, I wrote the wrong letter for transitive. Sorry. You're probably going, what is she doing? It's transitive. That's letter C. Number 6, if ST equals 2 and SU is equal to ST plus 3, then SU equals 5. Okay, so I have ST equals 2 and SU equals ST plus 3, then SU equals 5. What is that going to be? That's going to be the substitution property. We've substituted values there, okay? Look at number 7. If the measure of angle K is equal to 45 degrees, then 3 times the measure of angle K equals 135 degrees.
Symmetric.
Nope, look at it. What operation did I use right here?
Multiplication.
Multiplication. So that's going to be the multiplication property. And then finally, the measure of angle P is equal to the measure of angle Q. Then that means the measure of angle Q is equal to the measure of angle P. And that will be symmetric. Okay. All right. So let's take a look. It is 10:14. It is almost time to bail. So let's go ahead and look at homework. And so we will have pages 99 and 100. Actually, let's do 99 to page 101. Let's do numbers 10 through 32. 10 through 32. Evens, yes, thank you. Evens. So the first assignment was page 91 to 93, 8 through 48 evens. And this one will be page 99 to 101, numbers 10 through 32 evens. Okay,
And this
All right.
is Wednesday, correct?
this will be
Thank
due
you.
next Wednesday. Yeah, so when we return to class next Wednesday, it will need to have been uploaded and we will go over answers then. If you have any questions though, be sure to let me know. And I will plan on seeing you guys tomorrow at 8:30. Okay, I hope y'all have a great afternoon. Let me know if y'all need help with anything.
Bye.
Bye-bye, guys.
Thank you.
Bye-bye.